Namaste, good afternoon everyone. Welcome to the today's webinar on cutting the lab work by analyzing the microstructures with simulations. This webinar is organized by Paanduv Applications. This is going to be a live webinar and this is me. I am Dr. Rimzhim Gupta, the Senior Research Scientist at Paanduv Applications. I am available on LinkedIn. I encourage you to connect with me over LinkedIn to have some fruitful discussions on additive manufacturing. In this webinar, we are going to help you understand how can you cut down the lab work by analyzing the microstructures with simulations. Especially when I talk about simulations, I talk about AM PravaH, the simulation software for additive manufacturing, and the microstructure module of that. The company Paanduv Applications is established in 2020 by Advait Gupta, who is the founder and CEO of Paanduv Applications. He is an alumnus of Stanford University and NIT Warangal, India, and he is also the lead developer of AM PravaH. He has been involved in this process or in additive manufacturing field for the last decade. And the Paanduv Applications is located in Bareilly, Uttar Pradesh, which is in the north side of India, near the foothills of Himalayas. You can locate us through this map, and this is our head office in Bareilly. We are sitting in this office. This is a summer season, and the temperature here is around 33 degrees Celsius. So, very important question for today's listener is what is going to be there in this webinar? What do we get out of this webinar? So, first of all, I'll introduce you to AM PravaH, which is the simulation software developed by Paanduv R&D team, and the microstructure capabilities of the software. I will also introduce you to the experimental challenges in additive manufacturing, and particularly the challenges in microstructure analysis of metal AM processes. I will also then cover the microstructure prediction with AM PravaH. This will involve many case studies which are developed by Paanduv R&D team, and although the software is being used by multiple users and we have multiple user case studies as well, the primary source who are using the microstructure module of AM PravaH is NUS, which is the National University of Singapore. But keeping that aside, we are also going to cover what is the difference between EBSD analysis versus what you get out of AM PravaH, and we will have some concluding remarks on how can you reach out to us and how can we help you in uh, in uh, in procurement of the software and providing you the capabilities that we are currently working on, and this will also include some recent advances that we have made in the software. Very interesting anecdote that I want to add here is in 2013, there was the first implant that was introduced into a patient in New Delhi. It was just not a medical milestone, but it was a moment that showed that how and what AM can do when it is fused with digital design and laser precision. It is quite revolutionary, right? When we understand the manufacturing revolution, the first revolution started in 1784, where steam and water was introduced as the power sources. In the second revolution, 1870, where mass production started happening and electricity came into picture. In the third revolution, which is quite uh, quite history, in 1969, the electronics and IT systems were came into picture and automation started happening. This was a very important era for the manufacturing field. And fourth revolution, where we are right now, started in 2014, where cyber physical systems are introduced. The hammer replaced the hammer was replaced by the heat source. The molds were replaced by the models. So it's not just about printing the parts, it's also about reshaping how do we think about the strength, the weight, the complexity, and also the sustainability. Now we are in this era of Industry 4.0, the major components of which are augmented reality, big data, autonomous robots, simulations, system integrations, Internet of Things, cyber security, cloud computing, and additive manufacturing, wherein Paanduv captures the two important legs of Industry 4.0, which is additive manufacturing and simulations. In fact, both are coupled. So there are multiple breakthroughs people have obtained or attained so far, which in terms of topology optimization, people are using DFAM to obtain the topologically optimized parts. People are getting lattice structures, which are lightweighted components from using additive manufacturing, and generative AI is adding the extra cutting edge which is required in current times. Of course, there is a fourth leg, which is the digital twin, which combines the additive manufacturing to the simulations, but it provides you a complete replica of the experimentation, and there are multiple hierarchical processes which are involved in digital twin, which starts from creating a powder bed, melt pool dynamics, the microstructure evolution, and obtaining all the way to the part scale modeling. AM PravaH is a very important simulation software in that respect, because there are many processes, metal additive manufacturing processes, which are existing right now. And out of those, the most important ones, which are powder based laser bed fusion. Second is wire-based laser additive manufacturing, and the third one is wire-based arc additive manufacturing. The AM PravaH provides solution to all these three processes. When we are talking about additive manufacturing, we should also talk about the length scales it is spread into. At nanometric scale, experimentally, people do TEM, people do tomography, which are categorized as correlative microscopy. When you perform simulations for the same, molecular dynamics and phase field modeling gives you those insights that you gather from the correlative microscopy. When we go to the higher scale, from micro scale to millimeter scale, SEM, EBSD or synchrotron XRD gives you useful information which is very important to understand the entire process chain of additive manufacturing. But when we talk about the simulation strategies to perform the same, we have microstructure prediction and melt pool dynamics to perform the similar studies, gaining the similar insights that we are gaining from experiments. The last but not the least, when we go to higher scale, meter scales, we have part scale models. We develop parts experimentally, but what do we have? What do we want to understand through that? We want to understand the residual stresses, we want to understand the thermal data, and by that we are doing part scale modeling to understand, to get those insights. AM PravaH in its current shape is capable to handle the scale from micrometer scale to meter scale. That means we are covering microstructure modeling, melt pool dynamics and deformation studies using part scale models. Now, I will focus more on laser powder bed fusion, because this is a process which is very important, which is very likely for additive manufacturing folks to use. What is laser bed fusion? The feedstock used here is metal powder. When this metal powder is spread on the substrate and it is subjected to heat source, which is laser, there are multiple physics taking place at the same time. The metal starts absorbing the heat, melts itself and undergoes this melting, there are multiple other processes which are taking place, which are surface tension driven, which are thermally driven, and other multiple absorption based processes. But nevertheless, when the laser moves at the forefront, the melted parts start solidifying, and this solidification happens. This entire process is very important to understand because this is the root cause of defect formation. These are a couple of examples that I have listed here. The Rolls-Royce gas turbine, which is developed through this process itself. The steel printer pump components are produced through this process, and the SpaceX rocket engine components are also produced through this process. Ultimately, the user which is at the forefront of the machine, or the researcher or the process engineer, what do they want? They want to develop, they want to provide a sustainable technology to prevent the wastage. They also want to obtain the heterogeneous fine grain structures to produce a near net shape component. This is the final goal, where we obtain a component which does not require further processing. The final answer to all of these questions or all of these objectives is to understand the melt pool dynamics in good detail. This melt pool understanding will provide you the powder laser interaction insights. It will provide you the thermal profiles and gradients, interlayer adhesion, which can also be called lack of fusion defects. It will also provide you the shape and size of the tracks and what are the tentatively possible defects in for these particular parameters. Hence, it is very important to understand the melt pool dynamics in very good detail. The AM PravaH will elaborate on obtaining all of these insights by modeling the entire process chain of the additive manufacturing LPBF process. Finally, once you once you get the microstructures, you can correlate that with classical strengthening equations to obtain the yield strength. Now, simulations are also important to obtain some parameters related to temperature gradient and solidification rate. Why these parameters are very important? Because these, when you plot temperature gradient versus solidification rate, you will be able to understand in which realm your microstructures will be forming. This is a clear example of stainless steel, where by changing the process parameters, it can go all the way from cellular structure to columnar structure. This is another excellent validation and capability of additive manufacturing software to compare it with synchrotron X-ray imaging versus AM PravaH. This particular example is done for pure aluminium. Powder is not there, it is a welding case, and a laser is subjected at 500 watt at a laser scan speed of 1.2 meter per second, and the spot dia is 50 micrometer. And you can see a close correlation of simulation and formation of defect at exactly the same locations, and formation of keyhole by capturing the accurate physics, and this bulge is also something that you can see in the experimentation. It gives you an idea that complicated processes or complicated interplay between all of these parameters can give you a very complex physics, but simulations can handle that in good detail when you provide the right physics. With right physics, what I mean to say is that AM PravaH captures 4-phase multi-phase system, which includes vapor phase, molten phase, solid phase, and shielding gas phase, where you can exactly see how vapor plume ejection is happening and what is its interaction with the molten liquid. The other outcomes from LPBF simulations using AM PravaH can be multiple defects which can be generated either by keyhole. The porosity can be keyhole induced porosity or gas induced porosity or powder induced porosity. It can handle multi-layer simulations very well. You can see in this particular example, right hand side, left hand side, the bottommost, it is a 30 layer simulation, and corresponding to that you can see a thermal cycling plot which will give you an idea on how uh, what is the thermal history of this particular part. Another important concept is for laser additive manufacturing or laser beam shaping for additive manufacturing, where we have elaborated some Gaussian, some shapes of laser, which is elliptical, Gaussian beam, multi-Gaussian, Bessel function, top hat, ring beam. The elaborate concept of this particular laser beam shaping will be elaborated in our next webinar. And other defects such as vapor plume ejection, spattering can also be very well handled by additive manufacturing software AM PravaH. This is a very interesting example that is a product development by one of our users, which is IIT Roorkee. They have optimized the process parameters by using AM PravaH, and they have built this dental implant using cobalt chromium alloy that indicates that AM PravaH can be used for end-to-end product development and prototyping for additive manufacturing using relatively newer alloys. Now let's talk about microstructure. Microstructure, of course, is very important to understand, but what do we need in terms of obtaining the microstructure data? There are machines which are SEM, TEM, synchrotron based XRD machines, your FIB, your MicroCT. These machines are very important to obtain insights on microstructure, and the tentative idea on the cost per sample is around 5,000 USD, which is quite extensive. Now let's talk about microstructure, particularly in LPBF, and it is why is it unique? Now we understand that in LPBF process there is rapid solidification, rapid melting process, and due to which it has a tendency to form fine cellular grains. The cooling rates are in the range of 10 raised to power 6, 10 raised to power 7 Kelvin per second, and hence what you see on the screen is a relative scale of microstructures obtained by optical microscopy, SEM, EBSD data, HRTEM, and TEM images. Just to summarize, what are the challenges with microstructure data and how can we counter that? The primary challenge with microstructure data and obtaining that data is it is quite difficult in data acquisition. It requires advanced microscopes, as you have seen in the previous image. It requires in situ monitoring for the process, which is quite difficult without high-end facilities, for example, synchrotron-based processes. It is quite time and cost intensive, and defects can occur due to process parameters and which are not uh, elaborate which cannot be seen without using these high-end machinery. Now, what is the solution? What is the solution to that? I would recommend, or the additive manufacturing community has recommended, that you need to simulate before you print it. We need to engineer the process parameters in simulation to achieve defect-free surface. We need to understand the melt pool dynamics well in advance to obtain the defect-free surfaces, and we need to solve the governing equations using dynamic temperature fields or kinetic Monte Carlo simulation, and that is the solution to that. And we'll show you how this solution, how this proposed solution will help you obtain the defect-free parts. Now, a very useful information for all of you folks, that AM PravaH so far was available in research licenses form for research purposes. But now we are also introducing teaching licenses of additive manufacturing software AM PravaH for institutes or universities to procure in bulk licensing scheme, and they can use it for learning and teaching purposes, because I believe that today's young generation and today's learners are tomorrow's future changers. They are the game changers. So we need to step up and we need to teach people additive manufacturing in their classrooms, and that's why this is our initiative for AM industry to introduce physics-based simulation in their coursework. We have some limited offers for the people who have joined with us online and they are attending the webinar, and I will ask them to reach out to our team to inquire about these offers and get advantage out of it. Now I will hand over the floor to my colleague and he will take over the microstructure module in detail. They will involve some case studies, some validations, and it will be very interesting, I believe. And I'll hand over the floor to him.
So hello everyone, I am Abradeep and I will be navigating from now, and we will be discussing here the different facets of additive manufacturing microstructure module of AM PravaH, a simulation software from Paanduv applications. I will start with my introductions. So I am Abradeep and I am a material scientist working here at Paanduv Applications. I have my backgrounds with the additive manufacturing and the experimental microscopies. I have my background with the composite material manufacturing, and I have my backgrounds with the microstructure and process simulations, including the additive manufacturing processes that we have been doing here at Paanduv Applications. Coming to the microstructure evolution, for our microstructure module that is offered by Paanduv Applications, herein we will be delivering our microstructure module wherein we can show the spatial and temporal evolution of the microstructure. It includes the kinetic Monte Carlo model and Rosenthal's equation to generate the microstructure module. In this particular slide, what you can see is a microstructure that is formed for the 3-layer 3-track stainless steel 316L composite, wherein you can see we can easily dissect the different planes of the microstructure so that we can have an effect of tomographic data that we can attain from such type of analysis without delving us deeper into the 3-dimensional EBSD, which is quite a rare machine that we can have in most of the academic institutions. So combining this kinetic Monte Carlo modeling with the Rosenthal equation, we provide a description of the microstructure developed during the process. So in a synopsis, what it provides us with is a 3D tomographic information along with the microstructural informations, which are the grain boundary distributions and with the grain sizes. Typically we can have different sort of sections that we generate through the EBSD data, and we can have a complete microstructure description with this particular software module. Some of the recent advances in AM PravaH software includes crystallographic texture. As we all know, having a crystallographic texture data without using an experimentation like EBSD or bulk texture analysis has been a challenge since its inception. With this particular advancement, what we have developed the we track down the misorientations from the kinetic Monte Carlo and we put it in a stereographic plane and we achieve this crystallographic texture data. We also have added another additional capability. Instead of using Rosenthal's equation to improve our microstructural accuracies, we can take the temperature gradients, we can use the thermal histories generated during the melt pool dynamics. Melt pool dynamics has been a USP of Paanduv applications since its inception. In this module, we have simulated the melt pool dynamics first, considering all the physics based considerations, including the Marangoni, including the recoil pressure and all those elements, and we included those temperature fields and we take out their gradient and we generate this sort of microstructure evolution. I will be navigating for the further slides using the case studies and validations that we have done to showcase the capabilities that we have in our microstructure module at AM PravaH. For the case study 1, I will be considering a optical micrograph. So in general, when you have an additively manufactured component, we take it out and we do the basic microscopy. Instead of going to the EBSD based analysis directly, we can simulate the process. What we can do, we can have a nominal optical micrograph, we can measure the physical height and physical depth and width of the melt pool, and we simulate the entire process and we can generate the pool of microstructures, a pool of molten metals, so that we can have what we have here is a single build, that is a single track analysis of the melt track for this particular module. So we can see here the width and depth analysis from the experimental and the simulation, and the error percentage that we have in our case is way below 5%, which is quite accurate. Taking these dimensions to be followed and using the Rosenthal's equation, we have developed the entire microstructure for 5-layered and 4-track simulation. In this particular aspect, we have studied the grain nucleation driven by the Monte Carlo model, which is a probabilistic model, so that we can generate the non-stochastic behavior of the additively manufactured microstructures. We can also see the subtle details that are captured here by using the fundamental equations. What we can see here, that grain growth that has happened for the for a certain crystallographic direction has a certain anisotropic characteristics. We can see some subgrains have formed in the front face of the melt pool structure. We can see here the microstructure that is developed here has a columnar front as well as some sort of needle-like cellular prismatic structures that has some epitaxial nature. We can also see that we have the grain size charts which can be used to dictate the Hall page strengthening, and using such equations we can have some idea about the yield strength and we can predict the strength of the composite or strength of the material before we actually make it. Coming to the visualization part, in the visualization part we can see here I have sectioned the microstructure in such a way that we can see the 5-layer development here along with the 4 tracks, and we can see how accurately it has captured the transitions from the columnar to equiaxed in between the 2 successive melt tracks. We can also see the laser trajectory that it has followed alongside. We can also see the crystallographic texture presented in using the inverse pole figure without actually diving into the EBSD analysis. We can also see for this entire simulation, the computation time here is around 18 hours for a 48 cores machine. Such types of simulations have a great accuracy, and it also holds a thermal history quite accurately depending upon which the microstructure evolution has happened. That's how we have captured the not only the spatial development but as well as the temporal development. So these are the basic outcomes of from this study, is that using an optical micrograph we can calibrate the melt pool dimensions, and therefore we can develop our own parameter sets that can be used for the optimization and narrow down the window, so that we can know how our operation should be, whether it should be in a conduction mode or in a keyhole mode. That we can determine easily. Based on that, we have developed the melt pool dynamic simulations, wherein the temperature fields and gradients we can calculate and track down for the Monte Carlo approach. Using this approach, we can form the entire heterogeneous microstructure that are commonly observed in additively manufactured metals, and therefore what we have is the complete description of the microstructure that is formed in the AM process. Therefore, we can confirm that AM PravaH microstructure module can be treated as a virtual twin for an exact microstructure evolution process. We can also predict the crystallographic texture and also predict the grain size. Therefore, it won't be wrong to say that we can shift the length scale from an optical micrograph to the EBSD level without considering that experimental challenges that actually occur, such as the data acquisition and data analysis part with the different sort of softwares that we generally do in our regular microstructure analysis. It gives us a shortcut, or it gives us a complementary data. That's what we are trying to come up with AM PravaH software. Another validation case study that I would be discussing here is that how accurately we can capture the melt pool dynamics, and also from that melt pool dynamics how accurately we can predict the microstructure simulations. In this, what we have a data that we have collected from a publication. Herein we have a certain microstructure that is developed for a single exposure, single spot in a laser powder bed fusion process. In this, we can see here the EBSD data shows there are some non-indexed points, and therefore there are certain areas which are not actually covered here quite properly. Alongside, we have the AM PravaH simulated microstructure. We have tracked down the entire melt pool dynamics, and for each and every point we have calculated the temperature field. Those temperature field data was collected and exported into the microstructure module, wherein we have converted that data into the conventional route, so that we can have a complete description of the microstructure morphology. Based on that, we have analyzed how the grain growth can be predicted and how it can be done, and how the microstructure simulation can be performed, so that we can have the closest of the accuracy. We can clearly see the analogy is quite remarkable. It has not only captured the uncaptured regions from the EBSD, that is the non-indexed points, but also it has captured the entire crystallographic texture that we can see that has developed in the EBSD microstructure. Herein I will be discussing about the mechanism. You can clearly see with the images here that how these multi-phase simulations are useful to decipher the actual microstructure evolution. You can see here how the microstructure analysis gives us the detailed insight about the formation of the microstructure, in which we can see how the vapor entrapped gas pores can be modeled using the four-phase multi-phase system that we generally use. To summarize it, we can clearly see what we have done is the high fidelity melt pool simulation, followed by the dynamic temperature field and solidification field data collection. Along with, we have used Monte Carlo nucleation and growth approach, and then we use these dynamic temperature field variables coupled with the Monte Carlo simulation to generate the entire microstructure. We can see how precisely it has captured the uh, different aspects without considering um, any sort of aberrations here in the microstructure simulations that we generally see when you go for there are different sort of artifacts that generally appear in X-ray imaging and that sort of practical characterizations that actually causes data loss in certain cases if the data is not properly well analyzed. Also here we can see the computation time for such a great simulation is only 4 hours for an 8 core system, which is quite common these days. And this sort of simulations actually shows us how accurate we can go and how accurately we can capture the entire starting from the thermal history to the microstructure evolution. It captures the entire phenomena, and that's something that makes AM PravaH a phenomenal software. In a nutshell, what AM PravaH can do for metal additive manufacturing field is basically it uses the melt pool dynamic simulations and of the processes such as laser powder bed fusion. It can be any process that we have already demonstrated, like it can be LPBF, it can be WLAM, or it can be WAM, wherein we can solve the entire fundamental equations using the CFD approach and the basic and the fundamental approaches, and then we solve those fundamental equations and come up with the with the accurate melt pool dynamics without having any assumptions. Another predictions that we have done so far is the microstructure evolution, including that factor wherein the core is the dynamic temperature field gradients, which actually makes the data quite accurate. We can also see the crystallographic texture and grain size information that are trivial for the EBSD analysis only. Some other capabilities of AM PravaH microstructure module includes the microstructure evolution of using the Monte Carlo approach, which is a probabilistic model. Unlike other different microstructure models like cellular automata, it is not a deterministic one. Therefore, it gives us more clarity towards the probabilistic nature of the heterogeneity in the that are observed in the additively manufactured microstructures. It actually gives us a correlation between the process parameters and the microstructure information that you can correlate. The crystallographic texture is another insightful area that without getting into the complexities of the texture informations, which are often difficult for the users to analyze, we are directly feeding it into our systems so that it can not only generate the microstructure but also giving us the information about the orientations of the crystallographic orientations. Generating a microstructure from the dynamic temperature fields has been a great opportunity for the users so that they can put the same idea to not just the laser powder bed fusion but also the other manufacturing processes such as WLAM and WAM. This is something that actually provides us with the capability to be a digital twin of the entire additive manufacturing process. Other benefits that we have with AM PravaH includes it provides an end-to-end solution for the additive manufacturing process. That is, we are covering from powder to a part scale simulation. We can cut down the cost fundamentally by around 67%, and considering the initial process optimizations and other aspects that covers repeated trials and errors industrially and in the research principle. Also, we have 20 to 30% of cost saving in the material side, because with Paanduv applications, different approaches, we can not only simulate the spherical ones but also we can simulate different morphologies of the powder. That actually helps us to predict the microstructure and the melt pool dynamics of the non-spherical and irregular powder shapes. It can also reduce the failure rates up to 10% depending upon the recent capabilities that we have started with the FEA based approach, which includes the part scale modeling. So with that, we can, coupling with the microstructure data, we can have some idea about how the failure phenomena can happen. So based on that prediction, we can design our material and we can design the processes in that way, so that we can save it from the failure, premature failures. It also saved the experimental trials quite significantly, because we can see here that without getting into different experimental methodologies, we can actually simulate that entire structure before we run into the microscope. It Therefore, we completing this, we can definitely say we can emerge ours as an virtual twin for the additive manufacturing process here in as an industrial process, and as a potential tool for research in additive manufacturing. Here are the several users of AM PravaH. Here we can see the different global institutions that have acknowledged and recognized our contributions. Here are some defense organizations who have worked with us and are our happy customers. And we have some industrial collaborations and industrial customers from AMACE and InSmart Systems. I would like to thank my audience. I would like to thank my colleagues with whom and whose support has been and I am thankful to them for their unwavering support that they have provided for developing such innovative modules and developing such innovative work here at Paanduv Applications. Thank you. You can request a demo for our particular software by clicking on that link below that is added to the description. Thank you very much.